So by now this is probably seeming hopefully a fairly straightforward process here, but we're sort of given our observations. So we have these two readings from two different DNA samples, and we have to ask what is going to be relevant to weighing the evidence for this match versus mismatch situation. And they differ basically in whether we think that the two observations pertain to the same person or not. So we have to ask ourselves what's going to matter here in terms of this strength of evidence based upon our observations. So we have to be thinking both about what could connect the observations together under these two different modeling scenarios. So let's start with the match model. Under the match model, what would connect our two observations together? So what is the match model assuming? Yeah, it's assuming that they're from the same person. So can we turn that into a random variable that is sort of hiding in the background and producing these two observations? What would we propose would connect these two observations under this match model assumption?
X and S are both dependent on like kappa.
Right. So basically when we say that they're from the same person, we've got to put some kind of random variable here representing the genetic state of that person, and then both X and S are going to get connected to that. And what you just proposed, basically, this sort of count of the number of copies of this marker that's present in that person, that's probably the simplest possible random variable that we could propose for describing their genetic state for this particular marker. So we can basically throw in this random variable representing the person's genetic state, and then we can basically provide an edge there for that. So now what about in our mismatch model? If this is our match model, as we're assembling it, not necessarily done yet, but under our mismatch model, what should connect together this X and S? Okay, so you're saying sort of by extension, we'd have genetic states for people two different people, and they're going to connect these to those observations. So at this point, are we done? Is there just no connection between these two sides, X and S, that we need to take into account? Sure. So, so you're making this point about the frequency here. So, actually, I'm going to capture this since it's useful for us to just hide that for a second. This is a way for it to save it to the video for the. All right, so so we've got these two different models here. match and mismatch. So you just propose that what would connect together our X and S sides here is up above here we're going to have some, let's say, frequency for our genetic marker in the general population, and then that's going to affect both sides here. So the question I want to point out here is, why are we introducing this random variable theta as being important for our match versus mismatch models? So let's think about the effect. Let's say we were talking about some kind of situation where we've got a really rare genetic marker, and now we're looking at our observations whether we see it in our samples X and S. So I guess one basic point, hopefully, would be that if our frequency of this marker is really, really low, it's really, really rare in the population, that's going to change how likely we would expect seeing it in both X and S, right? So the proposal then is that since the population allele frequency would really affect our interpretation of what we see in X and S, depending upon whether the marker was a really common marker, maybe 50% of chromosomes have that marker, versus a really, really rare marker, maybe 1 in 1,000 chromosomes have that marker. That really should affect our judgment between match versus mismatch. Because, for example, in the case where it's a really, really common marker, it's not that surprising under the mismatch model. You're still going to have a high likelihood of seeing situations where you detect it in both the X sample and the S sample, just because it's a really common marker, right? So one way of saying this then is that when we start putting observations into an information graph structure, we have to ask ourselves, what is it that connects them in our different models? So here, it was almost immediately obvious what connects them, namely that they're supposed to come from the same person, so we got to have some random variable representing that genetic state, and it's going to connect our two observations. It might have been a little bit less obvious here in our mismatch model, but still just as important, actually, for these models to really take into account all of the different kinds of effects that really determine what the strength of the evidence for these two competing models is. Okay? So there's a modeling principle here that I'm proposing to you that basically you've got to think about what connects your variables, and in particular, you're given some observables. You've got to think about, well, what's going to connect those observables together under my different model candidates. Okay? So we're connecting them with theta over here in our mismatch model, so we need to have theta in our match model as well, so that we're really comparing sort of apples and apples in these two scenarios.